Hi everyone, we are from Group C, and me and my teammates will be presenting our mini project about this one research paper entitled A New Encryption Algorithm for Color Images Based on Total Chaotic Shuffling Scheme. I will be introducing our group member. We have NURHAYATI HASBI, which is me, hi. Secondly, we have GABRIEL Dennis. We have Debora Grace Rongod. We have BRYAN Ong. We have NATASHA AYUNI. And lastly, we have MOHD.ADIB ZUHAIRIE.
And let us introduce this chaos-based cryptographic scheme. It is an efficient encryption method first presented by Matthews RAJ. It has excellent characteristics that differ from other algorithms, such as sensitive dependence on initial conditions, non-periodicity, non-convergence, and control parameters. In recent years, various encryption schemes based on chaotic map have been proposed, and our research paper is research about the new encryption algorithm for color image based on total chaotic, total shuffling schemes.
Hi, my name is NURHAYATI, and I will be explaining the objectives of the paper. The main objective of the paper is to create an encryption algorithm based on quantum chaotic map, nearest neighboring couple map lattices, and also permutation diffusion architecture. In order to achieve the main objective, a key stream is generated to permute the pixels of RG and B components simultaneously, which causes the three components to affect one another, and this is done by quantum chaotic map. Secondly, random circular sheaf operation is performed. This results in permuted pixels to rearrange bits of each pixels. Finally, the new algorithm further diffuses the connection between the cipher image and the plain image by using the key stream produced by the nearest neighboring couple map lattices. And to generate the initial condition and parameters of the chaotic maps, a 128-bit long of external key is used. To conclude, the proposed algorithm has a high security level and high sensitivity that can be used for network security and secure communication.
So now I will continue with explanation and demonstration of the proposed crypto system. So the explanation and demonstration consists of two parts, whereby the first one is the generation of initial conditions and parameters, and second one is the proposed encryption algorithm. But before we move on with the generation of initial conditions and parameters, we will first take a look at the quantum chaotic map, since we will use this often further in our process and also for the proposed encryption algorithm. So the first equation, which is in the following diagram here, is the quantum chaotic map equations. So what is actually a quantum chaotic map? Quantum chaotic map are also called as the dissipative quantum systems are often described as a system coupled to a path of harmonic oscillators to construct a quantum logistic map with quantum corrections. The next equation is the nearest neighboring coupled map lattices, which is given as follows. So we will often further use this also in our generation initial of conditions and parameters, and also our proposed encryption algorithm. So as we can see here from the equation, J is equal to the lattice state index, N is the time index, F is the chaotic map, and E is the coupling coefficient. Now we will start with the first part, which is the generation of initial conditions and parameters, are also called as the key generation. For the generation of initial conditions and parameters, it is basically based on an analysis from our two previous equations that relies on several initial inputs that's shown in figure 1. So these initial inputs generate pseudo-random keystreams using the quantum chaotic map. So the proposed crypto system utilizes a 128-bit external secret key, K, that divides into 8-bit blocks, referred to as session keys. The K is defined as the following third equation. Then the initial inputs for image size, which is weight times height, will be given as the fourth equation as follows. So as we can see here from the first equation, which is from the quantum chaotic map equation, the beta is located in the negative exponent of E. So since it is located there, when beta is a large number or a larger value, the value of Z and Y will tend towards 0. So it means that the 3D quantum logistic map, or also known as the quantum chaotic map, will transform into a one-dimensional logistic map that has a smaller space or lower complexity. So it is also a reduction in the complexity of the encryption key, and it reduces the sensitivity of algorithm to the secret key. Therefore, to prevent the negative effect in the proposed algorithm, the variables xn, yn, and zn are coupled using the nearest neighboring coupled map lattice, and hence the secret key stream is generated. As we can see here in figure 2, this is the overall process for the key generation that has been explained previously. And now we will continue with the second part, which is the proposed encryption algorithm that consists of 7 steps. For the first step, we will apply k and set n equals to 0, L equals to W times h, or weight times height, R equals to 3.9, and beta equals to 4.5. And then we will generate the initial conditions as in the fourth equation as shown. So for the second step, we will apply the initial values from the previous step into our first equation, which is the quantum chaotic map, and we will obtain these 3 key streams, which are xn plus 1, yn plus 1, and zn plus 1. So to increase the complexity between the generated key streams, the equation 2 is utilized to couple generated key streams as follows in the fifth equation here, and it is generated into the range from 0 to 255, and hence it will produce the sixth equation as follows. And now we will set n equals to n plus 1, xn equals to xn key str, yn equals to yn key str, zn equals to zn key str, where n is iterated less than L. Third step, we will select W, which is the values from our previous generated key streams, and insert them into vector M and sort it to obtain M prime. Then we will then find the corresponding elements from M prime in M and create a vector index with values from range of 1W to 3W. Fourth step, we will use the elements of the matrix index and permute the rows of matrix P and obtain matrix P prime. Step 5, we will decompose matrix P prime into matrices, which are R, PER, W times H, G, PR, W times H, and B, PR, W times H. Therefore, we will obtain the CSR, CSG, CSB equation, where we can see from 7th equation here, and by using this 7th equation, we will substitute it into our 8th equation as follows to shift the 8-bit elements of matrices, where our n is equal to n plus 1, and we will iterate this step 5 until n is less than n.
The next step is diffusion. Firstly, we need to set n equals to 1, rc equals to 0, rci equals to 0, gc equals to 0, gci equals to 0, bc equals to 0, bci equals to 0, and lastly xrgb equals to 0. Then we will get the below equations where sr, sg, and sb are the summation of blend pixels after the n pixel of RGB component. For proper substitution, S box or substitution box of AES is used to get the equation that we can see on the screen right now. Step 7. Transform encryption is applied, so we will get the equations that we can see on the screen right now, where original value of n pixel, summation of blend pixels after n pixel, generated pseudo-random values, summation of encrypted pixel before the n pixel, summation of encrypted pixels before the n pixel of each component are used to encrypt the n pixels that we can see on the next slide. These are the equations that are used to encrypt the n pixel. The last step is matrices is transformed to get the colored image.
There are 5 examples, which is statistical analysis, sensibility analysis, informative entropy, key space analysis, and randomness test for the cipher. For statistical analysis, this histogram of encrypted image must be different with the histogram of original image. This is to prevent any clue or any hint to the attacker to break the original image. The correlation of two adjacent pixels is to analyze two adjacent pixels in vertical, horizontal, and diagonal in the image, and this pair of adjacent pixels can be calculated by this formula. For sensibility analysis, the first one is differential sensitive analysis, MPCR and UACI. MPCR is calculated and unified average changing intensity, while UACI is to measure the average intensity of difference between a plain image and the ciphered image. This is the formula of MPCR and UACI. Second is security key analysis. The encrypted image must be connected to the secret key, because a small change in the pixel can change the image totally. And lastly is avalanche criterion. Theoretically, a change of 1 bit in the plain text can cause the difference of 0.50 bits in the encrypted picture. For information entropy, this is created by Shannon, the information entropy hypothesis, which may sum up as the following formula. And the purpose of this method is to provide an acceptable entropy value, and it's far nearer to the optimum value of 8. So if the value is more closer to 8, this is become more acceptable. And next is key space analysis. The key space analysis is refer to the all possible combination of key that can be used in encryption to prevent the brute force assault, and we can assume that an effective encryption system have a sensitive to the security key and have a big range of the key space. For key space, it is referred to all possible combination of key for encryption, and this is used to prevent the brute force attack. So the effective encryption system has a very sensitive security key and have a big range of numbers of the secret key. And lastly, the randomness test for the cipher. The common test and the randomness of encrypted picture can be examined by using die-hard, NIST SV20503 and the ENT test suite. Each test has the subtest to examine the randomness of the different parameters.
So we move to the result. We have three concepts here. The first concept is a die-hard test. The second concept is NIST SV822, and the third concept is ENT test. We will see the result for the three concepts here. This is for the die-hard test result, and this is the table, and you can see here the result is a success. All the tests, the result is success. And then this is for the NIST SV822 test, and this the table, and as you can see here all the tests for this NIST SV822, the result is success. And we move to the last test, which is ENT test. And then this is the table, and as you can see here the test and the result, all of the result is a success too. So that's all for this test. So an examination of the result of this test clearly indicates that the purpose image encryption algorithm successfully passed all the tests. That's all from me.
As a conclusion, the new algorithm that was generated by using a quantum chaotic map diffused the relationship between the cipher image and the plain image. The proposed method is faster than other encryption processes. Lastly, the simulation result demonstrated satisfactory performance was achieved in the proposed algorithm.